let's try the recording again. We left off talking about, this whole chapter was graphing equations, getting familiar with how the calculus corresponds to the visual. A model could be increasing at certain periods of time or decreasing. It could have a local max or min. And the application of that was to talk about optimizing and finding an absolute max or an absolute min given a specific situation. So last week, before the break, we focused a lot on like word problem practice. And today is going to be a different type of application, another application with derivatives. Okay, and this corresponds to section 3.6. We're going to be skipping 3.5. We're not going to do 3.7. This is the last section that will apply to us from the book. And so with chapter 2, what we've done is all the mechanics of an average rate of change, an instantaneous rate of change, which we called the derivative, right? And then we spent the rest of the time trying to get better at finding the derivative instead of using the long definition with the limit as h goes to 0. Right, so we came up with some rules to help us out. We talked about a power rule, which applies to taking a derivative of something to an exponent. We said drop the exponent, subtract 1. We talked about the derivative of e to the x, which, what is that derivative? E to the x. And then we also talked about the natural log derivative, which is what? 1 over x. Okay, so this was the exponential derivative, this was the logarithmic. Okay, and then we talked about other rules, like if I combine them, like if I add or subtract them, then how do I handle a derivative? And we said, well, just do the addition or subtraction of each one separately. We said, well, what if I just want to multiply by a number out front to any one of these? Then what would the derivative look like? And we said, okay, we'll just deal with multiplying by the number later. We then talked about, well, what if I have a multiplication of these two functions? Right? And we had to come up with this special rule to help us out with that. And we said, well, if I'm multiplying functions, it's not as simple as adding or subtracting where I can do them separately. I have to do the following to get the accurate derivative. And then we did the same thing for division. But we had to square the denominator. Right, with the quotient rule. What was another rule that we talked about? Chain rule, right? So how did chain rule work? Yeah. Good. Yeah. So if I had a function inside another function, I want the derivative. Then we said, okay, you do the derivative. Let me do 2 colors just so we can see it easier. Do the derivative of the function like you normally would, but because this will contribute to the rate of change, we need to tack on the derivative of the inside, right? So whenever we had a function inside another function. Okay. So the when we moved on to the chapter 3, it took this idea of rate of change to talk about, well, how does that correspond to what the graph looks like? So the major application we did was chapter 3 being application, right? We saw how the calculus of a graph. In terms of increasing, decreasing, local maxes or mins. We talked about how is it increasing and decreasing with concavity. Right? We talked about inflection point, when it changes concavity. Another application we did was optimization, finding the absolute max or min. And our last application today is going to be something called related rates. Okay. And so this section, it's called Implicit Differentiation and Related Rates. Alright, so what does that mean? We kind of talked about this idea before, right? Let's say we have our revenue, which we know depends on how much stuff we're selling, right? Our revenue is x squared minus 2x plus 100, right? The money brought in when we sell x units. If I looked at the derivative with respect to the number of units sold, right, then what does this tell me? What are the units of that? Dollars per unit, exactly. Per unit sold. And that could be useful for us to know if I sell one more unit, how can I expect my revenue to change? That's definitely useful. But something that we pointed out before was how much we sell depends on time. Okay. So let's say our x, which depends on time, looks like I might be interested. So again, this is just an example, right? We want to know the change in revenue over time, not just per unit sold. At this point in time, in this month, in that year, how can I expect my revenue to change for one more month, right? And so how would you go about doing that? Okay, and you take a derivative. And so I have x in my revenue equation, but I want to get dr dt. And I'm given this equation. Okay, so let's write revenue instead with time. That looks like And so now when I want to do the derivative with time, okay, how would you do this derivative? Chain rule, right? So we do the derivative like we normally would. We bring down the 2, the new exponent is just the 1. This inside stays the same, but chain rule says I need to tack on the derivative of the inside, so what would that be? 3, good. How about here? Be minus 2, but I need the derivative of the inside, and so what would you get from that? 3, and then from the plus 100, it just stays the same. Okay, so okay, we need to use chain rule to do that. This section says, well, what if you weren't given an equation for the model? What if we don't have an equation? An explicit equation for what the variable depends on. Okay, so going back to the dr dt, where I have right, and x is equal to some function of t, I just don't know what it is, right? Some function just not given an explicit equation. Okay. Right. When we did this derivative, our function was x squared minus 2x plus 100, but x was some other function, we just didn't know what it was, right? Chain rule says if I have a function inside another function, right, I have to use chain rule. Okay. I want dr dt, but my equation that I have depends on x. I'm looking for a different variable, it depends on something else. So what I do is I treat this function like I normally would with the chain rule. The chain rule says, this is some function, I don't know what it is. I'll do the derivative like I normally would. I have a 2x with an exponent 1. But then chain rule says you have to tack on what? The derivative of the inside, right? I don't know what that derivative is, but I know that it has to go here. That's where the chain rule puts the derivative of x. How about from the minus 2, what would 2x, what would you get from that derivative? Minus 2. But this is some function, I just don't know the actual equation for it. So I would normally from chain rule tack on the derivative. So I'm just going to write that to represent where it would go. Okay. The 100 would be 0, so I don't need to worry about that. What's the revenue compared to time? That would be the equation for it. It's exactly what we have here. It's just we don't have the specific equation for the x and the derivative of x. Right? This idea of, okay, even though I don't have the equation, I still know how the steps work, I still know how chain rule works, is called implicit differentiation. Because I don't have an explicit equation, I'm doing it with the understanding that it's there, I just don't know the actual equation. So this is a derivative done using implicit.
And this is the answer for this example.
I'm sorry?
And this is the answer.
And that would be the answer, yeah. Another example. Let's keep the idea with revenue. Let's say it was okay, and we want the change in revenue over time, not change in revenue over X. So it's depending on a variable that we don't know how it's related yet. We don't have the explicit equation for it. But we still know how the steps work, right? X is some function. I don't know the actual equation for it. The derivative of it I can represent with that notation. And so I'm just doing what I'm asked to do, which is do the derivative with respect to time. This is the relationship I'm given. If I know these rates of change, I could plug that in later. But how would you do this derivative then?
So when we're doing it'll tell us what relationship we want. When we say d over dt.
Yeah, it will say d over dt. Yeah.
Would you just bring the 1/2?
Uh-huh.
And times 1.
Uh-huh.
So this one.
And then what's the new exponent?
Minus 1.
Okay. And x is some function of time. I just don't know the explicit equation. So chain rule, right, this being an unusual input, would normally have me tack on the derivative of the inside. And so what would you just write for that to represent that derivative? Be careful. D of, x over d of t. I don't know what that derivative is, but that's what it would be. That's where it should go. Right?
I have a question.
Yeah.
If it was in parentheses like 2x,
Yeah.
like 2x minus 1,
Uh-huh. Then it would say
do
2.
2 times dx over dt.
Perfect. Yeah. Exactly.
Because it's what the derivative is inside is all times the dx.
Yeah. Exactly.
So for this specific example with revenue,
Yeah.
using revenue, like say if we had a different example, wouldn't be d over t as a third, like we wouldn't be as the third variable. You have the d over t.
Yeah.
If you're using time, that's how you get revenue.
Yeah.
But it could change up on any of the other.
Yeah, it could just depend on the situation. So like we're gonna do a few practice problems with that. I have a handout for you all. But honestly the handouts just make it a lot easier to understand what it's saying. Let me go ahead and give that to you all now.